Okay, this is a oral history interview for Professor Bogy at UC Berkeley. This oral history records Professor Bogy's contribution in three areas: the establishment of a very successful computer mechanics laboratory at UC Berkeley, a joint university industry research center, and his research on HDD-related topics, especially in the areas of tribology, head dynamics, and simulations, and various measurement techniques related to head-disk interface, and educating many students that went into HDD industry to make key contribution to the HDD technology. I hope that is a short introduction. So I'd like to begin this interview by asking you about your background, family background, where you were born, grew up, and where you received your education.
All right. It was quite a ways from Silicon Valley. I was born and grew up in a small farming village in southeastern Arkansas. And I went through the first 10 years of my education at the school there. This town had a population of about 325 people. And I got my first 10 years of education in a school there. Typically, I would have 7 to 10 people in the class. And I just did the first 3 years in the same room with the same teacher. So it was fairly a low output organization. I went there through the 10th grade and then transferred to a prep school in Tennessee, actually, called Columbia Military Academy, and I graduated from there. From there, I went to Rice University, and I received 2 bachelor's degrees there, one in mechanical engineering and one in geology. Sort of the reason for that was somewhat unusual in that after my second year in mechanical engineering, I took a summer job in industry as an internship. And this was in Indianapolis at General Motors, and they made aircraft engines there. And I saw just acres of engineers with slide rules designing turbine blades for jet engines. And so it seemed to me like that didn't appeal to me a whole lot. So when I went back to the university to start my junior year, I decided I'd change my major to geology, and because I was more of an outdoor person. And so I changed my major to geology, and I almost completed that degree. I was in second semester of senior year and decided I'd made a big mistake. so I changed. I went there, and one of the great things about a smaller university like Rice University, they didn't just kick me out. They said, well, okay. He said, one thing that works in your favor is you've taken math every year, even though that wasn't required. And so if you take in your second year, your senior year, 7 courses, 5 of which have labs, and complete those, and then go to summer school and take 3 more required courses, then you can come back as a senior. You can finish the geology and come back as a senior in mechanical engineering the next year. So that's what I did. And so after 5 years, I had completed both of those degrees. And then I stayed there for a master's degree in mechanical engineering. And after that, I had been in ROTC, so I was obligated to go into the Army for 6 months, actually. But so I went there, and first to Fort Belvoir, Virginia, and then to Fort Leonard Wood, Missouri, and just as I was about to get out, there was the Cuban Missile Crisis. And so I was told I needed to stay an extra year. And so that meant I had to stay there another year. And after that year was up, there was a Berlin Wall crisis. And they said, oh, we may have to stay another year. But finally, I was let out. And then I worked for Shell Research, Shell Development Company it was called, in Houston for a while until I could go to graduate school. I went to Brown University to study mechanics. Actually, it was called applied mathematics there, but it was really applied mechanics anywhere. And so I went there to work with a particular professor who was well known in the field of elasticity. And when I got there, he was actually not there. He was on a one-year sabbatical leave in Japan. And so when he came back after that first year, he agreed I could work for him. And but after a short time, he advised me he was leaving there and going to Caltech. So I said, oh, well, maybe I'll just go with you to Caltech. And he said, oh, well, but so then it was worked out, well, if I finished my courses and passed my qualifying exams, then I could go to Caltech and do my research. And so I did that and went to Caltech. So I was at Brown about 1.5 years, and then I went to Caltech and did my research there. I finished my PhD there, and after about a year, and then I stayed as a postdoc in Caltech and applied mechanics. So that's pretty much my education.
So when you were growing up in Arkansas, were your family in farming or something
Oh
else?
yes, my father was in. He was a partner in a company that owned a farm and also a sort of a large general store and a cotton gin.
Wow.
They raised cotton in those.
So it was quite a big, good-sized enterprise.
Yeah, it was an enterprise. So actually, almost all of my teenage years, I worked in the field, drove tractors, plowing the ground for cotton and soybeans and things of that nature.
I see.
So it was quite a bit different from my later life.
But so you were interested originally in mechanical engineering.
Yeah.
So how did that come about?
Well, I can't say my life has been very planned. It's just sort of happened. So I first was going to go, my sisters had all told me, oh, I should go to the University of Arkansas. And so the summer after I graduated, I went to some fraternity parties around to see how that was at the university, and I found I definitely did not like that. And so one of the persons who was there told me, he was a student at Rice, and he said, well, if you want to be serious, why don't you go to Rice and study engineering? And so I decided, well, yeah, that probably sounds more like me. So I contacted them at Rice, and oddly enough, they allowed me to come. I had not contacted them before that summer, so they allowed me to come there. And so I went there and somewhat lost, and I just kind of fell in with some other students, and they were going to be engineers. And so I said, oh, okay, yeah, well, I'll be a mechanical engineer also.
I see.
And that's how I got into mechanical engineering without knowing much about it. And so that's why after 2 years, I decided, well, maybe that was a mistake.
What was it about that you decided you didn't like mechanical engineering?
Well, it was that summer internship where I saw what mechanical engineers were doing. I decided that didn't seem like my life, to be cooped up with a bunch of people trying to sit there all day and operate slide rules.
I see.
So you know, I changed to this geology and enjoyed that. We had summer trips out in Colorado where we'd go and peck on rocks with hammers and things like that. And so, but the thing that got me out of that was that in my senior year we studied seismology, and typically geology is a descriptive science. It's not an analytical science, and so it was rather hard for them to teach seismology in that way. And so in going through their course in seismology, I realized that I would like something a little bit more rigorous. And so because it was impossible to understand wave theory and wave propagation and earthquakes and all of that without knowing some mechanics and mathematics. So that's why I decided I had made a mistake. I was
see.
more inclined
Again,
for that.
change back. I see. And you say you were an ROTC.
Yeah.
So right from the beginning, you decided to do that.
Well,
at the school?
actually, as I said, my last 2 years of high school was in a military academy. And
right.
so basically I was in ROTC when I was in high school. And then when I went to college, I was sort of in third year ROTC already as a freshman. And so
it seemed like a natural thing to do.
It just looked like a good thing to do. I mean, most people sort of figured they somehow had to go in the military in those days, and it was, things were a bit unsettled in those times. There were rumblings already about Vietnam, and I figured better to be an officer than a private.
You didn't, so you really didn't have to go overseas or anything like
No,
that?
I never did actually. Once I got out, I was obligated to be in the reserves and to go to summer reserve camps for several years or something. But somehow, I didn't do it. I don't know why or how. But so after I got out in Fort Leonard Wood, after my year and a half in, that was pretty much the end of it for me in the military.
So you worked for Shell, and that was oil business. That didn't suit you either, or?
Well, that was sort of related to my geology and my mechanical engineering, in that I was working in what they call their production research, and it had to do with oil well drilling and seismological prospecting for oil using seismology and activities like that. But mostly I worked in the mechanics of oil well drilling. And the first papers that I've written had to do with vibrations of drill strings caused by drill bits that were grinding around on the bottom of rocks and things of that nature, and stability of them too. These drill strings, one drills hole a couple of miles deep in the earth, and they are a lot of heavy steel, and they're unstable in a lot of ways. They buckle and twist, and there's a lot of interesting mechanics problems that take place in that area. So I worked in those fields and had a few papers in that area.
Oh, you actually wrote papers?
Yeah, actually,
Wow.
I worked with a person who actually inspired me a lot at Rice University. His name was Paul Pasley, and he had come there, and he was so excited about his work that it was contagious. And so I got into, we worked together in that area when I was working at Shell. He also was consultant at Shell, and we worked together in that and wrote papers in that area.
So that's, but then you decided to go to Brown. What was the reason for choosing Brown?
Again, it was this professor that had sort of inspired me, and so the question arose, well, should I stay at Rice and do a PhD? And he said, no, you should go somewhere else. You shouldn't get all your education in one place. And so he said the best place to go was Brown. and where they had a lot of activity in this area that I was interested in at that time. And he knew it very well, and so I applied to half a dozen universities, including, I guess, 3 on the East Coast and 3 on the West Coast, the typical ones, the MIT and Brown and, I don't know, maybe Cornell on the East, and Berkeley and Stanford and Caltech in the West. So, but he told me Brown was the best place for me to go, and so I went there.
So I know your advisor was this Eli
Sternberg.
Sternberg, very famous guy, right?
Yeah.
Did you pick him right away, or?
I went to Brown, as I said, to work for him. My advisor at Rice had told me that based on what I was interested in, he was the right person for me. So as I said, I went there specifically to work with him, to only find out that he was away for the
He wasn't
year.
there, but he still took you and got going.
Yeah, when he came back, he took me as a student, as I said, and we started working in a certain area, and then he said, well, he's leaving, going to Caltech, which he did do, and I went with him. Or I went like a few months later.
So my understanding, this Professor Sternberg is very famous elasticity guy.
Oh yeah, he was in linear elasticity.
This is very theoretical and highly mathematical.
Yeah. That was it. That was my education in graduate school. As I said, my degree was applied mathematics, and it was applied to the area of mechanics.
So that kind of topic suited you.
It was purely theoretical. Yeah.
Right, but you know, I mean, I seen some of this coursework on this. Is very dry.
Yeah. Well, it was only dry if you didn't like it, you know. But
you were very much interested in this.
I liked it, yeah.
I see.
So it was quite exciting, yeah.
I see.
Yeah.
So so specifically, what sort of topic did you do your work on?
Oh, at that time?
Yes.
Oh, we were working in a couple of areas. At that time, and this was a sort of a very interesting time in the field of mechanics, and at Brown University had a whole collection of professors who were very big in that area. There was a professor, in addition to Sternberg, there was Rivlin, and there was Shield, and several others, and there were all kinds of seminars and activity. It was a very exciting place at the time. But at that particular time, there was a new field called, there was sort of a revolution in the area of mechanics, going back to the fundamentals and trying to get everything squared away. And so they began looking at what's called higher order strain theories, coupled stresses and things of that nature. And so these new theories were coming about. So Sternberg was very interested in elasticity, and in particular, and also at that time in these coupled stresses, and also in stress singularities caused by various discontinuities or material interfaces or things of that nature. And so I worked initially in that area, these coupled stress theories. And,
I see.
And eventually, skipping forward a little bit, but eventually down the road when I was in Berkeley, I was also one of the senior professors there, Paul Nagde. They were working in these director theories, which had some similarities to the coupled stress theories, and working with them in connection with all kind of structures and plates and shells and actually water waves and fluid jets. And I eventually applied that theory to inkjet studies, which I'll get into a little later on when we get to that part. But these coupled stress things eventually had some application.
I see. So from Caltech, you did some postdoc. What was that?
That was, I worked, well, actually, I just go. My thesis work was rather esoteric problem that I was able to solve in this in the theory of elasticity related to it's called Saint-Venant's problem for cylinder. And Sternberg, working at Caltech with a professor named James Knowles, they had proved that all of these more or less solutions that came about, their approximate solutions that came about for things like long cylinders, there were solutions for extension, bending, torsion, and flexure. And they had proved that there were that the particular solution for those problems were the optimal solution amongst a class of solutions that might satisfy those conditions for all except the flexure. And they didn't prove it for the flexure, or at least they proved there was one for the flexure, but they couldn't solve that problem. And so they worked on that for, I think, a half year or something. And it turned out then that my work wasn't going so well in this couple stress theory. I kind of got bogged down in that. And so I said, well, let me have a go at that problem that you guys have been working on. They kind of set it aside. And he said, well, okay, you can do that. And so I sat down and started scratching my head and working on it, and day and night. And finally I got this idea. And
a solution.
I got this idea, and it paid off, and I was able to solve it. And so Sternberg said, okay, that's your thesis.
I see.
That's all you have to do. Because he was impressed by that. And so I wrote that up and published it. I don't know if anyone ever cited it or not, because it was rather esoteric.
I see. So this postdoc work was with Sternberg also?
Yeah, right, yeah.
So just continued.
Yeah, it's pretty much continued what I was doing. And then we went back to the couple stress business and started looking at the effect of couple stresses on some stress singularities that occurred in certain plane solutions in elasticity, to see if maybe they would do away with these singularities or something like that if you included these extra ingredients into the theory. And so, I solved several of those problems, and we published papers based on those, published a few papers based on those. It wasn't all of that successful, in the sense that it didn't do anything that gave great insight into the world of mechanics.
So I imagine back then there was no simulations or modeling. It's just all partial differential equations.
Well, it's interesting that you say that. Back then, there was, of course, numericals. One would solve problems usually using Fourier methods,
I see.
Fourier series methods, but you still needed to do computations. Mm-hmm. And so the computations were either slide rules or machines, like they had these Frieden machines and Marchant machines that, they could add, multiply, subtract, divide, and take the square root. That was the extent of their capability. And it took a long time. But
Right.
Anyway, one still had to do computation. But in those days, and later on when I got to Berkeley, when one did computations, one was very careful about what you were computing, because it took a lot of time to compute, right? So
On mainframe. And
yeah, oh yeah. That was then when I got to Berkeley. Then we working like that. Yeah. Mm-hmm.
So I just want to touch on Professor Sternberg. He's a very interesting guy in his own right. Did you get to be very close to him?
Well,
was it
I
just-
don't know. Probably not real close, but close enough that I was I and one other person were his only graduate students at that time, because he had just come there from Brown, and he started getting up. And he didn't have a large research operation. He was always funded by the Office of Naval Research.
I see.
And he did his totally, you might say, esoteric theoretical studies in mechanics that you would wonder why the Navy would be interested in it. But anyway, they in those days, funding was for basic science that people did, you know. I got to be as close to him, I think, as any of his graduate students ever did. I mean, he would, for example, I would see him fairly regularly, go to his home 2 or 3 times a year for some kind of party or dinner or something like that. And but, you know, that's pretty much, it was pretty formal. He was like, you know, I was, I was in my late 20s, and he was in his late 60s, so.
He was a refugee from Vienna or someplace.
Oh, yeah, he had come, yeah, during
the war.
Yeah,
well,
he
just
had
before
come,
the war, I guess.
Yeah, probably before the war. He had come and done his PhD, I think, at an IIT in Illinois, Institute of Technology. And then he was on the faculty there. He worked with a professor there named Sadowski. He was also a theoretical elastician. And then he went to Brown and joined that group, that large group in mechanics. Yeah.
So, let's see. So after your postdoc, you went to Berkeley.
Yeah, I decided near the end of my postdoc that I would pursue a career in academia. So I was office mates with another person there, and we kicked it around back and forth what we were going to do when we graduated and all. He decided to go to work for Los Alamos. He finished and went to work at Los Alamos, and I said, well, I think I'll go for academia. So fortunately, at that time, there were quite a few faculty positions available. I interviewed again at few places on the East Coast and a few places on the West Coast. And I think I had 4 offers to be faculty member at MIT and Berkeley and UCLA. And UCSD was a very new university at that time, and I had some offer to go there. So the way I got, it's interesting, it was so different in those days than how it is now. There was a professor in our ME department. We had a division. It had a division of applied mechanics, and he was Paul Nagdi was the professor who was the head of that. And so when they had an opening, he would just go around to various known places and find people, or he would actually ask faculty that he knew at those places, hey, do you have any guy coming up that might be? And so he came down and interviewed me in Caltech, and we went out for dinner and hit it off pretty well. So he invited me up to Berkeley to have interview, and I came here, and I liked the academic climate and the weather climate. It was in February, it was a beautiful day. And so my wife and I decided, well, we'd go to Berkeley.
I see.
Yeah.
So you were already married by then?
Yeah, I was married. I had gotten married before I left Rice, yeah.
I see.
Yeah. My wife also, I met her at Rice, actually, so she was a history major there, and she finished there also. Yeah.
So when they hire you at Berkeley, did they have some specific thing? I mean, you were elasticity guy, so
yeah.
Is that what they expected from you? Or
yeah, I would thought course. Well, I was assigned courses to teach in mechanics, and I mean the job description at Berkeley was, and I gather still is, that you're half teaching and half researching. And so, you know, we were on a semester system, and we typically taught 3 semester courses per year, and supposed to do research and publish and and also what they call service on various committees and all this kind of stuff. And yeah, I taught undergraduate courses in mechanics like statics and dynamics, and graduate courses in elasticity and plasticity and things of that nature. So, yeah.
So this is late 60s or early
Yeah,
70s?
67. I went there almost exactly 50 years ago this month.
Oh,
So,
wow. 50 years.
I've been 50 years in
That's a
Berkeley.
long time. I see. So, what were some of the research topics that you
Oh,
picked up
well,
at that time?
at that time, of course, I started, before I actually had left Caltech, I had discussed with Sternberg some really important stress concentration problems related to interfaces and geometrical discontinuities and interfaces between materials and things of that nature. And so when I got to Berkeley, I thought, well, I think I will look into those problems. And so I started looking into those problems, and I worked on that really hard for the first couple of years. And I eventually published a few papers in there. One of the papers I published in that has turned out to be quite important. It's been cited more than 800 times
Oh, wow.
in the literature.
So,
But-
could you say a little bit about that?
Well, it basically was this problem. If you have, let's say, for example, that you have, say, a half space, and, or so let's just say this, suppose you have a half space, and it's really 2 quarter spaces that are glued together, and then you somehow pull on that. Then at the interface of the materials and the boundary, it turns out that according to elasticity, there will be unbounded stresses there. So that would be the place where failure would initiate. And so that turns out that was the first problem that I solved in that regard. And then after I solved that problem, another professor in Northwestern looked at my solution and said, hey, this has some real promise. He said, instead of that solution depending on 3 parameters, it really only depends on 2 material parameters. And so he defined those parameters. We've kind of published a joint thing based on that. And then with that, I could really take off. I could then solve the problem of any wedges of any angle and any materials coming together and forming stress concentrations at that interface, all the way around to where it became even if it were a crack between something. And so that's the paper that I wrote that I said has been
So there's a
cited
lot
more
of
than 8
practical applications.
Oh, it's very
for this,
practical applications. A lot of people even in in integrated circuits, and where there are a lot of material interfaces and things like that, and where there tends to be delamination, where there are things that be delaminated. You can typically, without a lot of effort, figure out based on some of the work I did what are the severe stress concentration situations and what are not.
So you had a pretty good start.
Well, yeah, so I worked on that, yeah. And then, yeah.
And I mean, you're doing mostly theoretical work. Did you need a lot of funding, or?
Well, I
or
was
you still-
funded by National Science Foundation.
Okay.
I applied for, in those days, which are different now, the foundations and the defense establishment tended to fund individual faculty that they somehow thought had promise. And so, you wrote proposals to the National Science Foundation. They get reviewed, and you get not a whole lot of funding, enough to support a graduate student and maybe have a 1 month summer pay, because at the university you got paid for 9 months, and the other 3 months were up to you. And so I did that, yeah. And so then I think your next question is, well, how did I get into
Yes.
this? And that's an interesting question to have, and it again comes back to myself, and that it was, although I was intrigued by this theoretical and highly mathematical business, it really wasn't quite me. As I said, I had kind of been more of I had grown up driving tractors. I was more of an applied type person, so I decided I wanted to get into more applied research activities. And an opportunity arose after about my third year to get a summer, it's called a summer faculty position at, it was at IBM in San Jose. And it turned out that was with Frank Tolka.
Right. Okay.
Frank had finished his PhD. The first year I was in Berkeley, he finished it. He finished his PhD in '68. I came there in '67, and he had gone to work there, and he had a group there doing mechanics and data storage systems. They were doing all sorts of things, and so I went down there that summer and worked with him, and it was great because he had all these experiments going, but no one was doing analysis on them. So I said, okay, I'll define and analyze these problems, and we'll see how it goes. And so that's what we did. We first worked on basically magnetic recording and flexible media. They were working on rotating head type systems, like it was in a VHS or something, but
So it was on tape, or?
It was on tape, yeah. Tape wrapped around a mandrel that had a rotating head on it.
Okay.
But it was for data storage, not for. And they actually, IBM actually had a library system made of those tape cartridges that had these rotating head devices on them. And the really interesting problem, from my perspective, was when you wrap this tape around something, it had edges. I mean, it eventually comes together, and so this rotating head, which has to establish its air bearing as it rotates, it comes to a place where there's a gap, and it loses its entire air bearing, and then has to start all over. So what was going on at those edges is what was interesting, and is what I worked on and analyzed. So.
Did you know Frank Tolka when he was a student?
Not really. He worked for a colleague very close. He worked for Stanley Berger in fluid mechanics, and worked in some rather esoteric problems, I think, on turbulence at the trailing edge of some boundary layer device or something. I didn't really know him. I might have known of him. And so it was kind of like when I went there to this IBM, and we kind of got together, and then we realized we had a lot of things in common and interest, in particular climbing mountains and walking in the mountains.
He loves hiking.
Yeah, right. Yeah. So yeah, we worked on those problems, and also on some linear tape problems also.
So this began your very long, fruitful relationship.
Yeah,
with
so that was the beginning. That was probably, may have been in 71 or 2, after I had been in Berkeley only about 3 years or 3 or 4 years. Yeah.
I see.
Yeah, right.
So how was it mostly with IBM initially?
Oh yeah, it was with IBM. So I did that 3 summers in a row.
I see.
And then in the between, I also was a consultant with IBM, and we worked on various problems.
During a regular year.
Yeah, right. During the school year, I also could work basically 1 day a week or something on that sort of stuff. And so that's actually how I got into that business of mechanics of data storage systems. And I had, at that time, I think, it then became possible, IBM had something they called graduate student fellowships. And so we could apply for that, and Frank would help apply for that, and I got one. And I think the first graduate student project I had on that was a person named George Adams, who's been a faculty member ever since he graduated at Northeastern University. But he worked on moving loads on layered flexible media, basically tape problem, you know. And,
so this was IBM. He was IBM guy.
No, he was my graduate student. at Berkeley.
It was funded by IBM.
Yeah, right.
Oh,
yeah,
wonderful.
yeah. And then I had another student. He probably finished in '75, and then I had another student, Richard Benson, who worked on. There was a floppy disk system that had a solid base. It was called a Bernoulli drive. You may remember something called a Bernoulli drive.
Yes.
And so Richard Benson worked on that problem and found some very interesting results. Essentially, that the equations that describe the waves in the disk changed their character in the inner region of the disk to the outer region of the disk. In the inner region of the disk, they were parabolic differential equations. The outer region, they were hyperbolic. And so there was a region where they changed. And that was something quite interesting. We did experiments on that also in Berkeley. And so that was he's now the president of the University of Texas in Dallas. There's a University of Texas. He's in his second year of doing that. So he's an interesting
He's done very well.
Yeah.
From Bernoulli equations to president of a university.
Yeah. So then I had another student, and we set up a lab. I didn't have a laboratory, but I kind of began setting up a laboratory at Berkeley, and there's this issue with regard to floppy disks in which you wanted to have high density and a lot of data tracks. And floppy disks were made out of mylar, essentially was the substrate for it, or polyethylene terephthalate it was called. And that is made in a big sheet, and it's extruded, and it's tensiled in both directions while it's extruding. So it ends up, it's not an isotropic material, it's orthotropic. It has two different axes of where its material properties are different, and it's viscoelastic. So the idea was this: you stamp a disk out of this web somewhere, either on the outside, the middle, or the inside, and it ends up not only orthotropic, but it's viscoelastic, and it also recovers. It creeps in a recovery because it has been stretched in its manufacture. So it creeps in a recovery. And so if that happens, then if you have recorded a circle on it and you put it up somewhere for a few years and you come back, it's no longer a circle. And so I did analysis on that. I analyzed that problem. And I think I wrote some IBM research, some papers in IBM Research and Development Journal. They had an IBM Journal of Research and Development. And did analysis of that. And they also set up this experiment in Berkeley and had this student who worked on that experiment. And so that's pretty much was the early days of working in that.
The IBM started to provide you equipment to do measurements?
Well, then we started, let's see, so I have to move myself forward into about 1980. I was working on other things at that time because, I had kind of gotten out of the theoretical elasticity, but I was working on and funded in an area of nondestructive evaluation. In other words, using elastic wave theory to detect flaws in structures. I mean, if you can imagine a large pressure vessel.
So this is completely not, this is your work at
Yeah,
Berkeley.
this is my work,
Other work,
my continued elasticity
yes,
work. I was
right.
still doing that. I mean, I
Right.
didn't switch over everything at once, right?
Mm-hmm.
So I got into something. So I was still doing that work in this non-destructive evaluation, and that was a fairly well organized, that was funded by National Science Foundation, and it was fairly well organized out of Iowa State University, some people, and we had these annual meetings down in La Jolla. And so I used to go there and every summer and take my family and kids and enjoy the beaches in La Jolla. We got to know UCSD quite well there. And but that was, I was doing experimental work related to that, as well in various issues. And so that kind of got phased out as the data storage business got phased in while I was doing that.
See. When did you start moving into the hard disk space? How did that come about?
Let's see here. It's interesting. And to me at least, in about 1980, 81 or 2, started looking at that, and I had this graduate student who helped me a lot at that time. His name was Denny Mew, and he helped me set up my laboratory. My first lab computer was a DEC PDP 1140. we set that up in the lab, and with dual floppies is the only storage it had, and started writing programs for doing calculations on various aspects of that. But he also set up, we were then interested in hard drive head disk interface dynamics. And so I started doing work in that, and he built in our lab a large, on a big isolation table, a large LDV system.
Wow.
Right? And we used that system to show that we could detect some slider in an old Seagate, first hard drive, Seagate hard drive. I've forgotten exactly what it was. It's about a 20 megabyte hard drive, 5¼ inch hard drive. We used that to show that, we actually took the top off and cut a hole in it and put a window on it, put a glass window on it, so we could shine down through it into the drive, and show that we could make some measurements, some interesting measurements of that. And
so like the first time, people were doing that type of work?
Yeah, it was the first time people were doing that. And then it turned out, my relationship with Frank Tonke continued, and we continued working together on those things. We worked on some other things too, though, before we got there. We also worked on inkjet printing.
Right.
I mentioned to you that I had,
Right.
that I probably was the first
Yeah.
person to ever applied this esoteric Kosarat theory to stability of
Inkjet.
inkjets. And we studied inkjets, first inkjets, so I'm kind of wandering back and forth, but it kind of all goes together. First inkjets that they were doing at IBM were what they were called continuous jets. And the idea there was they would spray a jet of fluid out of the head and actually put enough ink out to cover the page black. But they could charge every drop that came out. And so we charge a drop and then run it through some capacitance plates and could deflect it
Yes.
that way. So they essentially would send out enough drops to cover the page black and send all the drops they didn't need to write text off to a recycle path. And that was the first concept for their inkjet printing. And it had all kind of problems because they would get all jammed up and stuff. And so anyway, so we did a lot of work on that, and it was a lot of fun. But that eventually didn't win the day, and so it became something called drop-on-demand inkjet. So Frank had in his lab, had these drop-on-demand inkjet systems all set up there, and we could make these measurements. I would do the analysis of these drop-on-demand inkjet printers, and what that required is to extrude a jet is to just somehow kick out one drop when you needed it. And there were, initially, the technology was to have a little reservoir with a little nozzle on it and a back plate, and the back plate was a piezoelectric plate. And so you would just pulse that plate when you wanted to kick a drop out. And so that was the first scheme for the drop-on-demand. But then later came along both HP and Canon came up with this scheme of what they call a bubble jet. So they just had a little heater in it, and no one would have ever figured that to work too well, but they just had this heater in it, and they would shoot some power to that heater. It would immediately cause a bubble, and the bubble would then expand, and then that would eject the drop. And so that was another even more complex problem to analyze, but we worked on that one.
On that too.
Yeah. So that was sort of in the inkjet business. But then at the university, then I was beginning to get more interested in this hard drive stuff. And Frank spent the year 1984 in my lab in Berkeley, and we worked on those problems together with my student Denny Mew and another student, Gilles Bouchard. And we wrote 2 or 3 joint papers on that where we had, but Denny Mew actually was the first student that I had who then made a real impact in that area. And he got from, I think, Ampex. You probably know about this because this was the first thin film disc. They had something called an ALAR disc.
It's a plated disc.
Yeah, plated
Yes.
disc, ALAR disc. But they were somehow able then to sputter some little steps on those discs. So we had a well-characterized disturbance. And so
you can measure now.
Yeah, and so we knew what the step was, and we could do this experiment where we would fly this head across these steps and then measure the dynamics with this LDV. And so Denny Mew did that experiment, and he also wrote air-bearing software to analyze the dynamics of the slider under that situation. And that was really our first recognition in the area of head disk interface studies.
I see.
And
so this is like 1983 or 4.
This was in
Somewhere around
83. 83 and 80. Well, Frank was there in 84. So in 84. And then he finished his degree in 85, and he went to UCLA and on the faculty there. And he was more of an entrepreneur. He left there and formed some companies, and
I see.
that worked out well. But
Clearly,
anyway,
you have some really good grad students.
oh yeah,
also.
grad students the only way. That's the most important thing for a faculty member is choosing good graduate students. Yeah, because they teach you as technology changes. They teach you, and so that's.
So how could you say a little bit more about the LDV technology? How did you come to be aware of that and that you could use this?
Well, that's interesting. There was professor at Stanford who had published a paper on it, Cal Quate.
Oh, Professor Quate.
Yeah.
Yeah, okay.
Cal Quate. He had I think they call it the Applied Physics Lab at Stanford, or you probably know what that lab was, but Cal Quate was there. And he had published a paper where he had shown this laid out LDV system and had shown it making some measurement of something, a dynamic measurement of something. And so we got the idea that somehow that we could use that to make, and so I contacted him and asked him, could we come and visit your lab and copy your LDV system?
I see.
And he said, sure, come on. So I took my student, Denny Mew, and maybe one other student. We went down there, and we looked it all over, and went back and indeed copied it. Denny had also had some other experience with that from somewhere, so I'm not quite sure. But that's kind of how he got the idea.
Started.
It was a paper of Cal Quate's.
I see.
Yeah.
But you must have realized you could use this to measure some minute.
Well, yeah, I mean, so I
fluctuations,
think the idea was, in reading his paper, I've forgotten what it was now, but it said, that you could shine this on something that was moving and measure its movement. Down when the movement was only in the, nanometer range.
Right.
And high frequency range. And so,
It evolved to become one of the most key measurement tools.
Do what?
It evolved to become one of the key measurement tools.
Yeah, I think so. I think it's used. We use it. I have many systems like that in my laboratory right now. We use it all the time, every day almost, right? And I think everybody does too. Right?
So it must took some doing to develop all the lasers, electronics, and everything to go with that measurement.
At that time, we didn't have to develop it all. There existed a box, a phase demodulator we could buy.
I see.
So it was basically the optics and these phase demodulators, and then just software for analyzing it and
I see.
figuring out what it was. But that's where I relied heavily on good graduate students.
I see.
Yeah.
So moving on, you set up a computer mechanics laboratory.
Yeah.
How did that come about? When was that?
That's interesting also, in the sense that I guess if I look back on my life, very little of it was planned, laid out as a plan.
Okay.
It was always reacting to some opportunity. So in about 1980, the National Science Foundation began to change the way it funded university research. They said, instead of having all these individual guys out here doing these small projects by themselves that are unrelated to anything, we're going to set up these centers. They call it National Science Foundation's Engineering Research Centers. And so they announced that and told several universities, or anybody, to apply for these engineering research centers. And they said, in order for it, some of the requirements are that it have industry
Participation.
support.
Yes.
Somehow. And so we were by that time doing work in the area, as I had indicated, not only of inkjet printing, but also wire. There was a printing technique of where they had little wires that would peck on carbon papers.
I remember that.
Yeah,
yes.
some kind of wire printing, wire hammer printing, and then laser printing. There were a lot of good mechanics problems in laser printing. In particular, there was one called the cold fusion problem, where they had these rollers. And the interesting thing about the rollers and the stress concentration is you have a piece of paper that has to be rolled through two rollers and mashed rather hard between them and heated. The rollers were heated. And this was to sort of cure the printing part. And at the edges of the papers, there were stress concentrations. And they would eventually cause these rollers to fail, where, you basically wear them out, where the stress concentrations were at there. And so I had a student whose thesis was to analyze the hot roll fusion problem.
This was being funded by somebody?
Probably, it might have been funded by IBM, I'm not sure. The student's name was David Glaze. He eventually went to work for IBM in Rochester, Minnesota.
Oh, I see.
And he worked in that area. And then we had, so we were doing other kind of printing research, and we were doing, so the HDD work we were doing was called storage, and then there were some faculty in our department that were looking at problems related to integrated circuits, in particular packaging issues in integrated circuits, and we had some faculty in our thermal science area who were doing heat transfer problems, cooling, heat transfer, actually in hard disk drives as well as in integrated circuit issues. And so we decided, I and some of my colleagues decided, we will put together a National Science Foundation Engineering Research Center proposal and call it Storage, Printing, Packaging, and Cooling.
Okay.
And so we had faculty who contributed parts in that and all, and so we did a lot of work and got companies to, at least someone in a company who knew of our work, to write letters saying they supported this concept and this would be good. And so I had people at IBM and DEC and many other drive companies around. They wrote letters for us and everything. And so we put that proposal in, but we didn't get it.
Okay.
And so we didn't get it. But we had a lot of good contacts in industry by that time, right?
I see.
And some ideas about some stuff to do.
Maybe the name was too long.
Yeah, the name may have been too long, I think. And so then we kind of kept going. Then we started getting some funding from some other companies besides IBM to do stuff and equip. IBM supported us a lot, though, in those days with equipment, computer, workstations, a lot of workstations. We got workstations. And that was very helpful. And also these graduate fellowships. And they had also something called a faculty research fellowship or something that was just something these were gifts that they would give the university, so they weren't contracts or anything. And we got a couple of those and stuff. And we had some funding from other places. So our stuff was getting going, we were getting going. And so then something happened that was sort of interesting. At about that time, I would say in about 1981 or so, Al Hoagland and Jim Lemke, Hoagland at IBM, and Lemke at that time was president of something called Spin Physics.
Spin Physics.
Yeah, he had a outfit called Spin Physics. So Hoagland and Lemke showed up and said, we want to have at some university, we want to have at a university a magnetic storage center, magnetic center, and we want we invite Berkeley to write a proposal for it. of course, no one really knew if those guys had enough power to do anything like that. But they invited us to do that. They also invited Stanford to, and I think UCLA and UCSD to write a proposal to start a magnetic center at their university. So it turned out, so we wrote a proposal. We were the only of those universities, we were the only ones that are doing any work in magnetic storage and mechanics of it, you know. And so we wrote ours proposal as mechanics and magnetic storage, which included our work in head disk interface and also our work in some thermal work that was going on, and kind of put this together again. We kind of dusted off our NSF
Previous
proposal
one.
and shortened the name and put that in, and it turned out we didn't get that either. We didn't get that for a good reason, though, and that reason was that Lemke was very tight with Richard Atkinson, who was the chancellor at UCSD. And so whereas Berkeley wouldn't say we will cough up something for this activity, at UCSD they were promised a building and 4 chaired professorships for that, and so that center went there to become CMRR. And so it was established there, but there was nothing there. And so, but they got started. So they formed a committee. And this committee was for the CMRR. And I was initially served on the committee, as did some other persons. There was a person named Norm Talso, who I think had been at something called Magnetic Peripherals, which Seagate eventually bought, but he had been there. And there was a guy at IBM, I think his name was Butt, and 2 or 3 other people. So there was on this committee, and we were kind of get stuff going. Well, anyway, so they had some funding, and they were interested in having some research going on at universities, and so they actually funded my research in Berkeley with the CMR. The first research report written from CMRR was one of mine.
Was your work?
Yeah, right. and we wrote, I think we were probably funded for 3 years
Until
from
they
CMR.
get going.
Huh?
Until they get
Yeah,
going.
while they were getting going. And so they then offered me one of their chair positions there.
I see.
And because they had to recruit these faculty too, you know. So I didn't want to leave Berkeley, and so I said, no, I wouldn't leave Berkeley. But, you know, Frank was then in '84, he was in my lab, and I said, you guys should hire Talkie, you know. And so they tried for quite a while, and he was a hard guy for them to hire. But eventually he went there in '86, and he became their
So
guy.
you were responsible for him leaving IBM.
Well, I mean, you know, we had a great relationship at
Right,
IBM,
right.
and then he went to UCSD, and then we had a different great relationship when he was in UCSD. But yeah, he left IBM to become one of those chair professors down there at UCSD, and they got their building going and everything, and they funded work until they finally got their people on board and had to spend their money there. But then, so we're getting on up into the mid '80s, and we were beginning to get quite a bit of funding from various companies. And
A lot of startups and
a lot of drive companies and component companies. You know, head companies and disk companies. You know about the disk company and drive companies. So we decided, okay, we will start this computer mechanics laboratory. And so at the university at that time, there were quite restrictions on what you could call yourself. If you wanted to call yourself, so we first were going to call ourselves a center, because that's what they did at UCSD. They called themselves a center. So we said we'll call ourselves a center.
Right.
But it turned out in Berkeley there were very strict requirements on calling yourself a center, and you couldn't just call yourself a center. You had to go through basically a lot of legal issues and a lot of organizational, structural issues, and basically report to the dean and various other things like that, if you were going to be a center. And so we decided, well, I said, that's too much trouble. But you could call yourself a laboratory.
Oh.
They didn't have, in fact, there was something called an electronics research laboratory that had been very successful in the EE department. And so I said, I think we'll call ourselves the Computer Mechanics Laboratory. And so we chose that name, and then just went to these companies. I set down the rules for so we said we'll have membership, company membership. And so I drafted myself without any other organization in the university saying anything about it, what the terms of these memberships were.
Right.
And the biggest problem with working with industry at that time were patent problems, patent issues. Essentially, if the industry wanted to fund research at the university, they wanted to have, and if any patents came out of that, they wanted to have
Patent rights.
They actually wanted to own the patents at first. Yeah, they wanted to have the patents. And of course, I told them, I said, well, when I signed up here at the university, I signed an agreement that said if in my research I find anything patentable, I'm obligated to disclose it to the university patent office, So, but I said, so far I've never found anything I thought was patentable. And so that is up to me. So actually we had funding, I would say 2 or 3 times funding, even from IBM at the beginning, that was agreed on technically, agreed on by the source of funds, but the legal departments. So then they would get tied up with writing some kind of contract or grant between IBM and the University of California, Berkeley, and so all these lawyers would get involved, and eventually nothing came of it. And the patents were the main issue. Patents were the issue. And so I basically just told these companies, I knew people, I talked to people. I said, look, I have a very high bar in what I think is patentable. And so far, I've never written a patent. And so far, still, I've never written a patent. And I said, here's what our plan will be in CML. When we're doing research, when we find something that we think is suitable for writing a research paper, we will write a paper and we will submit it to a journal. And then the members of our CML will get that document at the time we send it to the journal. So that basically gives you a 6 months lead time on whatever we have found that we give to a journal. So that I said, I can't say that I won't write a patent, but I can say I haven't written a patent, and I don't really like patents that much. I think they kind of are not in the spirit of a university where you can share what you're doing with everybody, And so I said, that's my philosophy. And so I was able to write up this 3-page document that said what the benefit of a company would be to be a member of CML and what it would cost. And that it essential is this: we'll have a 1-year agreement, contract more or less, and you will pay a certain fund, you'll be a certain level member in CML, you will receive certain benefits, and if at the end of that year you don't like it, well, don't come back. If you do, well, we'll do it again. And so that's how we did it. And so
So
it
many
got going.
company did sign up for that.
What?
Many company did sign up for that.
In about 97 or 98, we had 26 companies that were members of CML.
Right.
All the drive companies almost except Toshiba. And all of the a lot of component companies, head companies, and media companies, and so it was really an interesting and good group. And we held these annual research meetings and held out. But we had some big problems in that area too, and I'd like to tell you about some of those. Some
Okay.
real
Or
problems.
maybe, I don't know if you want to do that now or talk about some other subject about the CML.
Well, I think it's in connection with starting the CML. It's part of starting CML.
Right.
One was I had traveled in Japan and had visited a lot of these Japanese companies. And so when we set up CML, I said, I want to have Japanese companies as members. And that caused a big problem because IBM,
They were paranoid about it.
they had just sued Hitachi.
Yeah, they are paranoia about
Yeah,
it.
right. And so there was a big fight in IBM. It went all the way. It went all the way to whoever was the CEO of IBM at the time, and that person declined to make a decision. He said, "You guys do whatever you want to do," and so it turned out that the product division was very much opposed to Japanese companies, but the research division was not. And so I basically just dealt with the research division of IBM and not the product division. But then, and so that went along for a while. And a lot of other companies also weren't too, it costs a lot. Some companies didn't join because of the Japanese
Because of that,
company.
right.
And not only that, I'll come to another point here. IBM said, we will not fund head disk interface work at the university. In fact, it was the case at that time that a person in IBM could not utter the phrase head HDI outside of IBM. And if they went to a conference or something, they wouldn't talk about it. And they could never publish anything related to that
Yes.
at that time. And that had to do with IBM's problems they had with the 3380, I mean, which you might have known about. But anyway, they said, we will not fund HDI work. I said, well, that's what I do. And they, and the other companies, they wanted HDI work, you know. So then I said, okay, here's what we'll do. We'll have 2 bank accounts in CML. One can fund HDI work, and one will not fund HDI work. And all of IBM's funding will go into the one that does not fund HDI work. And somehow they bought that, and it went like that. But then about that time, there was something else coming along. You may recall, since you were at COMAG at that time, I think, there was something called NSIC. The National Storage Industry Consortium, that was formed, I think, in 1991. 1991, they formed this National Storage Industry Consortium, and they specifically had national as its first word. And they said, we're not funding CML because you guys have all these Japanese companies in your CML. So we went along with that for a while. We attended some meetings, and it was I remember there was I think John Simon was the guy who was in charge of that, and there was a guy from Maxtor and a guy from Quantum. They were on this committee, and so they said, okay, we had this meeting in Colorado and said, okay, you come there and make your case, and we'll see whether or not we can fund CML. And so I made my presentation to those guys, and they said, no way. So they said, no way. So that went along for a while. But eventually that kind of broke down. And they came around and started funding our work. And eventually, as you know, they changed their name. They took the national out. They took the NSIC out, and it became INSIC, which meant information storage consortium. I think so. So then they did the same thing.
Japan set up their own.
They set up their version called
we had joint
SRC.
Venture, yeah, we had joint ventures, so we were in both.
Yeah, right. Well, now I'm sure you may know this, but a few years ago, only 3 or 4, they killed INSIC and started something called ASTC, which is Advanced Storage Technology Consortium. And since that time, they worked hard to try to make it include the Japanese SRC that they had. And so I think they've now combined those two, and it's now called it's ASRC. It was ASTC. Now it was ASTC. Now it's ASRC, and it includes the Japanese. And so I have been to Japan to give presentations in the joint meeting of that group now. So even though that the separation of the Japanese and U.S. companies has gone away, there's not much left of either. Right. So. Yeah.
So needless to say, setting up a laboratory that caused variety of issues,
Yeah.
but it was out of necessity too. I understand, right?
Well,
Yeah, I mean, you had to operate that way in order to just coordinate all this.
well, yeah. I mean, we had a laboratory. We had we had like 8 faculty and about 30 some odd doctoral students, graduate students who were working in that area. And we were doing all kind of work in there,
It's
and
quite
had
a-
all
quite
these
an enterprise.
20 companies,
Yeah.
26 companies or so that were supporting it, and we would go out and visit them all the time. And yeah, it was quite an operation, but it was really a lot of fun.
So I don't know about the other company, but I know what we wanted. We wanted your grad students.
You wanted what?
We wanted your grad students.
Oh yeah. Well, no, that's interesting. So the question came up, and when we put together CML, and for industry, I go to them and ask for money, and they say, "What are you guys going to be able to do for us that we don't do?" I mean, we have better laboratories. We're a lot cleaner. we know a lot that we don't tell. So whatever you guys are going to work on, you're not going to know what the current state of the technology is. So what is you going to give us? And so basically we told them that we will train students who are knowledgeable in this technology and who will almost certainly go to work for your companies. And we will do research in this area. And although sometimes, I mean, we will probably not know what's really going on in your company, but we will nevertheless stumble upon something worthwhile every now and then, and you will get access to it. And then I said, we will give you early access to any of our work, because as I told you, we will publish it in a CML report that you have access to immediately as soon as we submit it, have it ready to go. And so those are basically the only 3 things that we can. Oh, and then we'll have annual meetings where you can come here and we'll make presentations about everything we're doing, and we will get your feedback on what we should be doing. And although, since your membership is more or less in the form of a gift, you can't tell us what to do, but your feedback is important for us because we want to know what you want done. And so we would do that. We have all these presentations, and then we'd send out a grade sheet and ask all the people from industry to grade these areas of research and give it back to us. And then I would look at that and I would decide what topics to fund, because all the students would have also prepared a one-page proposal of what they plan to do next year. And so they would rank all these proposals, and we would use that information to fund our ongoing work. So I said, that's how it'll work.
I remember that many of our, top-notch engineers, will look forward to attending your CML review meetings more so than attending conferences.
Yeah.
Because it was that much more stimulating, and of course they get to see good graduate students.
Well, they were all eager graduate students, and as I said, we were trying to, we would have show and tell in our laboratories and have, PowerPoint presentations by the students. And so, yes, and we had one last year, but we're getting close to not, the number of members of CML presently, there are two drive companies, right? And all the component companies have been integrated into those drive companies. There's Western Digital. We actually no longer have Seagate since last year. And SAE, that's about it. So we probably not have to operate differently in the future.
So moving forward, what is your plan? I mean, doing something different, or?
Well, here's the thing. Moving forward, I don't know how much forward I have to go after 50 years. But anyway, I can tell you that I have, I don't know how to stop, really. I have 5 PhD students.
Still, wow.
I have 2 fifth year, 1 third year, 1 second year, 1 first year. I just took a brand new PhD student. And then I have a couple of master's students and a research engineer. And so I don't quite know how to.
I see.
I mean, one of the problems with this laboratory business is that you have to have continuity. You have to have senior students teaching junior students how to work all of this equipment and how to make all these measurements and how to run all these programs and stuff. If you ever break that train, it's almost impossible to get it geared back
going
up.
again.
Because I don't know how to do all these things that these students do, on a daily basis. But I know the higher level version of it, but when it really gets down to taking data in these things, I don't really know.
They all still work on the storage, or doing other things?
All of my students, well, now you're getting into current
stuff,
issues. They all in addition to those students that I told you I have 2 visiting PhD students and 2 visiting scholars, all from China. 2 visiting students, one from Tsinghua University and one from Xi'an, Jiaotong University, and 2 visiting faculty, one from Nanjing University, Science and Technology, and another one from Xi'an University, Jiaotong University. So almost all of us, are working on problems related to heat-assisted magnetic recording.
Oh, really?
Yeah.
I see.
And that's where the really fun problems are. And that's where the real important problems are.
Still difficult.
It's very difficult. And I don't know what its future holds. It's been promised as a product since 1912. I mean, it's in 2012. And now it's promised at the end of 2018. But it's hard to know
Right.
if it will be a product, and I'm sure that there's a lot of discussion around. There's so many interesting problems related to this, to it, though.
The degree of difficulty makes it for lots of interesting challenges, I guess.
Oh yeah,
I guess maybe.
I
As long as
mean,
you get funding.
what?
Long as you get funding.
Yeah, right. Well,
Okay.
people fund us for studying, working on that, and we've done some really interesting experiments recently. Now this is me talking. One of the problems, I believe, with heat-assisted magnetic recording is, and I'm sure you know this, so the idea of being able to get 10 terabits per square inch is that you have passed the super paramagnetic limit for perpendicular recording, maybe at 1 terabit per square inch, right? And so the question is, okay, so what do we do? And so the answer is, we get higher coercivity magnetic media. And you say, well, that's a good idea. The trouble is we can't write on it, right?
Let's heat
So-
it up.
So how can we write on it? Well, if you heat it up to its Curie temperature of about, 500 centigrade, and for a nanosecond, then you can flip its bit, and that will move on, and it'll kind of freeze in there, and you can write these data bits that close together with that high coercivity. And so that being the case, they say, well, yeah, okay, that's the way to go. And so as you probably know, that came out of, you probably remember the technology of Quinta and TerraStore. You remember those guys? They were going to do some optical recording, with some near-field transducer that
Right.
would allow them to overcome the diffraction limit of wave, of light. So there were these two companies, and they were going to do great things. They were going to do 10 gigabits per square. I think they were going to do 10 gigabits per square inch.
Yeah, I don't remember.
Yeah, and but before they could get there, the hard drives had already passed it up, and so that didn't work out too well for them. But anyway, I think that was the beginning of this heat-assisted magnetic recording, because Seagate bought that Quinta, and they set up in their research lab in Pittsburgh this activity of this heat-assisted magnetic recording. And one of the problems, I believe, is this, is everything now becomes nanoscale, right? So currently in hard drives that you go and buy, the magnetic spacing between the head of this, it's only 3 or 4 nanometers. And the physical spacing is like 1 nanometer. It's all controlled by this thermal flight control business, right? So, so then you start talking about having a laser that's sitting on top of a head, that's solid state laser, that's creating a laser beam going through a waveguide that's going down and to a near field transducer that is kind of an antenna of some type that's allowing this energy to be focused down to a 25 or 50 nanometer spot instead of using 800 nanometer wavelength light. And so there's a huge amount of heat that has to go, power that has to go in there. And you need to have really reliable heat transfer theory to deal with that. And it turned out that all of these systems have been designed using commercial packages, codes, that were not based on nanoscale system. They were based on microscale and above stuff. And the rules for heat transfer in nanoscale are different than they are in nanoscale. And so a lot of times they would have these near-field transducers, and they work for a little while and then they fail. And so that's been a big issue. So we've done some work on that. It hasn't been very popular because we've kind of been critical of some of it. And it's
Are you
cost.
doing a lot of these type of heat transfer theoretical type of work?
Yeah,
Oh, I
yeah.
see.
And so
I see.
that's it's cost us some support too.
Oh. Don't want to hear bad news. Wow.
But anyway, it's very interesting. I mean, it has everything to do with carbon overcoats, with lube, with reliability, and then there's some really good problems we're working on that you have. It turns out that they're getting longer and longer, the duration of life of these things. But one of the problems is that there's a lot of things that transfer to the head.
Right.
It's
very hot and
yeah, and it builds up on there, and it pretty soon it increases the spacing, and so
I think that's what happened to like Terrastor. The lens get all clogged up in a hurry. And
yeah, right. So anyway, there are a lot of great problems. We enjoy working on those problems. I certainly hope it's successful.
So I forgot to ask a question that of all the work you've done on HDD space, what are some of your favorite, one that you think had the most impact?
Well, I think it's interesting. This one, COMAG may have appreciated. I say COMAG because you didn't announce that you were formerly with COMAG, but I think everybody knows that. In about 1980, in the middle 80s, maybe 86 or 7, I had this postdoc, Shaw Tsai.
Sure, yeah.
Yeah, and we did this work on basically application of diamond-like carbon to for thin film magnetic media, and wrote this review article on it of essentially looking at
it was a massive
paper.
Huh?
What?
Massive paper.
Massive paper. And that paper had almost 800 citations also. It's been a very highly cited paper.
So you're very happy with that?
Yeah, so that was a very good result. And so after that, then we went into doing quite a bit of work. Did Shaw Tsai work for COMAG?
Yes, for a few years.
Yeah, I don't know where he is now.
Yeah, he was quite, in age already. So
yeah, he was pretty old when he was even with me. But
yeah, we hired him right out of
yeah, I thought
Berkeley.
you did, yeah. So there's another.
So that resulted in all this work on carbon, nitrogen effect, and all this type of work.
Then we went into this work on the effect catalytic reactions of lubes, and had a UHV system there in Berkeley. We also did some of it at Lawrence Berkeley Lab, but we had this system, and I had several graduate students. I think he may have gone to work for COMAG. We had these, we looked at the tribochemical wear of lubricants and using these UHV systems. And that was good work, I thought. We also, so I think the most satisfying work we have done has been in our, let me say this, though, that our one of the real things that a whole series of my students did all the way for the last 30 years was writing code for air-bearing design and slider dynamics
Right.
under various situations, including all the way up to ramp load systems and shock, taking into consideration all of the air bearings as well as the vibrations of all the structures and how they would get excited and do all that. So we had students that do. So I think that code, our members always had access to that code and someone to kind of talk to them about it when they needed. And so I think that was what really kept us in business, and because there were certain companies that relied on that code. I mean,
I think they joined the lab just to have your code.
to get the code. But they're the main companies. It's interesting. Say IBM did not rely on that code for their ABS design group, but everybody else in IBM relied on that code because the ABS design group didn't share their code with the rest of IBM.
Right.
So guys that were there, especially my former students who had gone there, they all used our codes and insisted on using our
That
codes.
was a major contribution, I mean, to the whole storage
Yeah.
industry.
So I think that was our biggest product in terms of keeping members and getting them to pay.
Right.
Because that access to our code, we learned early on to write our code so it would expire with someone's membership, and so that's what
I see.
we did.
Yeah,
so.
that was very smart.
So I think those, that I would say the LDV work, the code work, and then some carbon overcoat and disc, tribochemical wear type work, and then our other work. We did a lot of work in ramp load systems that people liked, and we did a lot of work in nano indentation of ultra thin films. As you know, when you get a film that's 2 or 3 nanometers thick, carbon overcoat on your magnetic media, to characterize that mechanically is quite challenging. I mean, typically the way to do is they want to measure its hardness. Okay, what's its hardness? Well, you poke something in it and see what kind of hole you get for how hard you poked on it. And it's plastic deformation. And doing that for a few nanometers is pretty challenging. So we did a lot of work in that early work and worked with this company, Isotron, and helped them actually develop their Isotron, their nano indentation system.
You work with these companies that, measurement company that, you helped to develop the science and code and everything else. That was probably very, very fruitful work as well, I imagine.
Yeah.
Yeah, a number of them, right?
Right, yeah.
Isotron.
Right.
I forgot there were a couple other ones that you work with very closely.
Yeah, with the digital instruments. We worked closely with digital instruments. The guy who started that was down at UC Santa Barbara, and we worked with them on that. And also up at LBL, they were doing a lot of work on that. There's some guys up there, that was all very, very interesting work. Yeah.
So those are key contribution that a lot of companies that wouldn't have been able to develop something like that, on your own, could go and purchase these equipment and.
That's also we worked closely with the WICO guy, with
WICO.
Jim Wyatt. And we had WICO system. We had Zygo systems too. We worked with the guys from Zygo. A lot of, I think we helped those companies get into the data storage companies. I mean, to sell their stuff to companies, because we did work on that, and we would display it at our meetings and stuff.
So I want to cover one topic. I remember experiencing your ground rules, for grad students, and so I remember still very clearly. You have very firm rules about, expectation and so on. So when you pick grad students, do you have some ideas in mind how you pick them?
Well, that's interesting. I mean, yeah, I do. I have definite ideas how I pick them, and my ideas don't agree with a lot of others. But first of all, I say there are three kinds of graduate students, just like every. There are those graduate students. You give them a broad picture of what it is you're working on, and roughly what kind of area you think they should be working on. And there are those graduate students that can then figure out what to do. And they can figure out how to do it. And they can do it, right? Then there are those graduate students who really can't figure out what to do. But if you tell them what to do, they can do it. And then there's the other ones that you don't really wish you had, and that is they can't figure out what to do. And if you kind of tell them what to do, they can't really do it. And so, they're not going to. So I want to have that first batch of graduate students. So you say, well, how do you get those students? Well, I get them by going by their history, their training, and their performance, where they've been, and looking at various things. And so what has happened then for me over the years is that almost all of my graduate students have been foreign students. In other words, we get a lot of applicants to our department each year for graduate study, and from the top universities in the world. So in China, so Tsinghua University in China is kind of recognized as a top university, right, in its technical areas. And we are in India. Well, certain of these IITs in India, they turn out top people. And so they apply here. They can't come generally unless they're supported completely, right? So I look at those top students. You take a top student out of a place like, you take a place like Tsinghua University, their graduating class may have 150 students in it, and their top one or two guys who have applied, especially interested. So you look at those students and you say, gee, those guys look really well prepared to do stuff. I mean, they know the physics, they know mathematics, they know laboratory work, mechanics, they know electronics, they know programming, they know all these things, right? And you say, these guys are really prepared. There's one drawback. They're expensive because you have to support them, and that includes non-resident tuition. So,
I see.
So a lot of professors look at the incoming graduate student pool, and they say, I don't want that guy. He's too expensive. So I say, I'll go for this guy. He's expensive, but I believe he's worth the money. And so I typically end up getting these top students from China or India, and they're just outstanding students.
I see.
And so they come here. We have these requirements that they perform academically, that they have to do well in their courses. They have to pass a preliminary exam. They have to pass these qualifying exams, all that stuff. These students that I get, they're 2 or 3 years ahead in these performance criteria.
I see.
And they're really able to go. So these students, that's how I choose the students. And so that's why when you come to my laboratory, you see Chinese students, you see Indian students and maybe a European or two or something like that. But I remember, of course, Silicon Valley is made with, I remember one time at Comag, you almost had to speak Chinese in order to operate there. It was something like that. But anyway, then when I get these students, then how do I do with them? I say, okay, in our lab we do experiments, we do modeling, we do program development, and we do various other things. And I say, I have this range of problems. So I tell my students, the first year, all you have to do is try to learn what it is we do. I don't care, you don't expect to do any research accomplishment the first year, just learn what we do. And make the best grades in your courses and take these prelims early and get ready for your academic stuff. And they do that. And then I say, you probably prefer to either be an experimentalist or to be a modeler or to be a program developer or whatever. And I said, I'd like to honor that preference that you have. And so then I just every now and then I got to have an experimentalist, and I tell this guy, look, you just got to have to be an experimentalist or something like that. But that's kind of the way I do. I get what I think are the best guys and then let them kind of go their way and help define their
Sometimes
stuff.
you have to, if they're a foreign student, you may not necessarily be able to meet them, before you get them, right?
I
or
have
do you?
for a long time Skyped them or
Oh,
WeChat them or
okay.
something,
Okay. So
and interview them. I
you do
interview them, yeah.
them,
And I have visited in China. I've visited students who I were going to take as
Scope
foreign
them out
students.
first.
Yeah, right, yeah.
Okay.
And so it's important that they be able to have good English. Almost all of them do now, but I can recall students that I took who had these TOEFL scores, Test of English as a Foreign Language. They had great scores in the TOEFL from China, and they would come here, and these guys couldn't speak English,
I see.
And so I remember I asked one, I said, how did you make such a good score on the TOEFL? He says, oh, that was easy. You just had to memorize 7,000 words. I said, okay, well, I learned from that I couldn't go by the TOEFL score. So I had to have some interview with them one way or the other.
Do you suppose that, is it in the U.S., is the education system not producing enough of good students, or is just the competition worldwide is very, very keen?
Here, there's a changed emphasis in what students want now. It's changed from wanting to really learn fundamentals to being an entrepreneur or to being an environmentalist or to do socially useful work, and not so much on getting in the laboratory and grinding out stuff that's hard, but these foreign students still do that.
Still do that.
Yeah, and they're still trained in that way, And I think it will change there also, but probably it's still okay. I still get really good students. As I said, I have a new student who came last week from Tsinghua University. The guy is great.
I see. Are you still do you still do work on other areas besides HDD, or are you migrating to new fields?
Well,
what is happening?
I'm having some thoughts in that direction, but I'm not sure. In other words, the HDD companies have sort of decided that a substantial part of their future is also in solid state, right? And to the extent that they're reducing their university support for HDD work in favor of solid state work. This MRAM has kind of become a popular thing. There are problems we could do there. There are mechanics problems there. There's heat transfer problems there, nanoscale type. We could find work to do, I think, in that area, and I've been thinking about it, but haven't yet decided if I want to do that or not. But I think I keep my eyes open in that regard, and if the opportunity arises where I think we have the expertise that would lend itself to productive activities in those areas, I think we would possibly look at it, yeah.
I see.
I mean, yeah, as you know, CMRR changed their name. So they're no longer a Center for
That's
Magnetic
right.
Recording.
The magnetic came out.
Yeah, right.
I just noticed that recently.
Yeah, and so
Times.
yeah, so I think they've made that move to go into some MRAM type work.
And your grad student, I mean, even with a storage type of thesis and work, they probably could go work anywhere.
My students, you had written a question about where do my grad students go. So I would say, and how many? I have supervised 66 PhD students and about 100 master students.
So far.
Yeah, I don't keep up with the master students, but the PhD students, about a third of them have gone to academia, and about the other 2/3 have gone to industry, and of those, almost all into the hard drive industry business. A few in other industries, but presently, in my recent students, I would say more of them are going to Apple and Google and places like that. The requirements on them there are really not as stringent as they are in the hard drive company, in the sense that they want people who can basically write commercial finite element codes and analyze stuff that my students can basically do without a PhD. But that's where they're going out there. And a lot of our students, as you know, there's been a lot of downsizing in the hard drive business. A lot of our students have left and gone to Apple. I probably have 6 former PhD students at Apple in the reliability group.
Oh, really?
Yeah. And
I remember Brian Strong was one of the early ones to go
he was
there.
an early one. He's manager of a group there in reliability, and he hired 3 or 4 other guys that were in Samsung when he hired from there. Brian Thornton and Walt Fong and 2 or 3 other guys. They have a group there, and same in Google. Google now hires these guys.
I see.
And the people in our CML who are doing servo automatic controls and servo stuff, they're going to these companies for autonomous vehicle stuff.
Right.
Yeah,
There's
so
a huge expanding field in this kind of thing.
right. So our students are just really well grounded and prepared and have great capabilities, and they don't have to go to hard drive companies. They know the technology more when they go to those companies, but they're able to go elsewhere.
And even become a university president.
Yeah, right. Yeah. Well, that person who's a university president, he went there. He had been dean of Virginia Tech, and he had gone to be dean. Prior to that, he had been a professor at, I think, another university. But he had gone there, and about to be their dean, and about 2 months after he got there, they had that huge shootout at Virginia Tech, and
that's horrible.
in the building that his dean's office was in,
I see.
and they had to evacuate that and everything. But he was a very successful dean there, and he got this job as chancellor at.
It's a big system too,
Yeah.
the Texas.
Well, he's not of the whole system. He's
Oh.
of this university. It's not the Austin campus. It's the University of Texas in Dallas, which is
okay.
one of
the
yeah.
branch universities.
Yeah, right. Yeah.
Okay.
Mm-hmm.
Maybe a few other questions left. I forgot to mention. You won some awards, like the Reynolds Johnson Award, and is there some other ones that you care to talk about?
I won some ASME awards related to, tribology was a big part of, they have a tribology division of ASME, and they have their top award. It's called the Mayo D. Hersey Award.
I see.
I won that award back maybe 20 years ago. I won an award, Reynolds B. Johnson.
It's
Reynolds Johnson had-
2011, I think.
Yeah, they had 2 awards. One still
2010.
exists, but the one I won doesn't exist anymore.
Yeah, unfortunately. 2010, I have it here.
Yeah, right. And I won some Seagate Award for some kind of contribution in data storage
I see.
stuff, and some INSIC awards for just doing the stuff that we were doing at the time. That was after we finally got over the hurdle of being admitted into the INSIC. I see. And I've won some university awards. University of California has they don't give honorary degrees. They give what they call Berkeley gives something called a Berkeley citation instead of that, and I won that award in Berkeley.
Is that recently or?
Oh, that was probably, it
ago?
should be in there, probably 2011 or something.
Oh, okay.
2009, probably 9 or 10. Yeah, Berkeley citation.
So it's quite an honor to get this.
Yeah, I was. Yeah, it was
You've
honored to
been
receive it.
50 years.
Yeah, I mean, after
they need
50
to give
years,
you something.
they got to have to do something for it. Right?
The last thing, I wanted to hear what you say about your hobbies and your skiing at your age, which is remarkable.
Well, I was, as I told you, raised in a rural setting.
Yes.
And when I was growing up, my father and other people around would take me hunting and fishing. So we did a lot of hunting and fishing. I haven't continued so much with hunting, but I continue some fishing. So I would say my favorite outdoor activities, I would say, has been skiing and just mountaineering, hiking in the mountains and climbing. Frank and I did a lot of rock climbing together. We did that, so that was a great thing for us. And skiing I used to do quite a bit. I had a place up at Tahoe there, and when my children were young, we'd go skiing all the time. When they left, we didn't go so much. So I started sailing.
Sailing,
I have had, for the last probably 30 years, boats in the bay, sailboats, and also had a power boat, fishing boat that I'd take out in the ocean, fishing for salmon and stuff like that. So they closed salmon fishing here, and I gave that boat to my daughter and son-in-law who live in Connecticut. And
this is Susan?
No,
Susan?
that's Rebecca.
Rebecca.
She's a doctor in New Haven. And,
okay.
And her husband's organic chemist there, but he's a big fisherman, and so they fish in Long Island Sound. And so I go there 2-3 times a year and fish with them in Long Island Sound. It's great fishing there.
What do they fish for?
Oh, they fish, it depends on the time of the year, but they fish for striped bass. They fish for bluefish. They fish for blackfish, and for black bass is a different one. And that's pretty much it.
You join them for fishing with them?
Yeah, I go there and fish with them often. I used to fish it. I'd take my own boat. That same boat, I'd take it out into the Farallones and fishing out in there.
Well, that's way out there.
Yeah, it's out there, yeah. And on my sailboat, we used to go out. I had my sailboat in Mexico. It brought it up from
Wow.
there.
Awesome.
And used to sail out often down to Monterey and up to Point Reyes and stuff. But then my wife didn't like the ocean waves so much. You get seasick. So we kind of stayed mostly in the bay now. We still sail it in the bay.
I remember you telling me a story this long time ago, but you told me you hooked up a sturgeon, big one, and it kind of dragged you around for a little while. And
well, I don't know. I hooked up once.
Something.
I don't quite remember that, but I had
something big.
Well, in Texas, when I have my sister has a big ranch in Texas that has a lake on it that got great fish, but it also has alligators.
Oh, okay.
And I hooked up with an alligator, and that was, and the boat was small, and so I got dragged around quite a bit until we got rid of the alligator.
I see.
But yeah, so we so boating and skiing, and then I like. I remember Tu Chin was a big boater. Remember?
Yeah, he loved fishing.
Where's Tu Chin now?
Well, he's retired and he doesn't fish anymore. But,
where's John Chin? He was my student in Berkeley.
He works for this Trend Focus.
Oh yeah.
They do mostly SSD, business analysis, that type of thing.
Yeah.
But anyway, I went fishing many times with Tu Chin.
Yeah,
so
I never went with him, but he and I used to talk about fishing stories because I knew he had this boat and he would go out fishing. He went out in the ocean too, right?
Yes.
Yeah.
I went to Farallones with him one time.
Right, yeah.
Just caught just one tiny little fish. After about, I don't know, several $100 in gas. Something ridiculous.
I went out there once with one of my students, actually. He was my programmer analyst, and we went out there and we were fishing, and we saw this huge, really weird fish, and it was up. It's called a sunfish, and he came up to the top of the water, and he looked like he had been cut half in two. Only his head half was existing, and he was around there. And
they can become very, very large.
Yeah, he was very big. And, I saw that. That's the only time I've ever seen one. We saw that one, and we also saw some great white sharks out there once. They breed out there.
So you don't look like you're ready to slow down anytime soon.
Well, I figure if you slow down, what do? You just you can't afford to slow down, right? Yeah. And
you got grad student to support.
I have a grad student. I have a 5-year commitment to the one I just took, right? So what am I going to do? But sooner or later, I have to. The thing that will go is the laboratory first, because it's the hardest to keep going. You can keep modelers going without a whole lot of effort, but to keep guys in equipment. We just bought, Seagate had a big auction sale this last week, and we bought some new oscilloscopes from them that have great capabilities.
I see.
Yeah, and got to figure out how to get that down, but it's something we need for our work right now.
I see.
Yeah.